Hello, good morning everybody. Today we'll have the class with on reactivity and effect of carbanion in the context of organometallic chemistry. Okay, so let's see the reactivity of carbanion and their relation with the organometallic chemistry. So we can consider two cases for the organic compounds. Say let us say one is having X, another one having linked with a M. Okay, where X is the electronegative, or you can say non-metallic elements, or you can say they are electronegative atom, more electronegative than carbon atom. Okay, and here M is the metals are mostly electropositive. Okay, more electropositive than carbon atom. So we have two cases. Let us consider one carbon linked with a non-metallic element, another one second case carbon linked with a metal electropositive compounds, electropositive elements. Okay, so the first case they are polarized like this. They are slightly negative, positive charge and negative. In this case, negative, and this line positive charge. Okay, metals are electropositive. Here are non-metallic elements are electronegative. So it is polarized like this. So from the first case, we can get carbocations, and second case, we can get carbanion. So what we want to show that this type of compounds, are very organometallic compounds are very versatile reagents, and their reactivity depends on the metals attached to the nature of the metal attached to the carbon atom. So by appropriate choice of the metals, we can have different types of organometallic compounds. So depending on the nature of the metals, the compounds can have different types of compounds. Say organometallic compounds of sodium and potassium are solid compounds, which are insoluble in non-polar solvents, and those of less polar elements like magnesium and zinc are essentially covalent and are soluble in, say for example, ether. And that is so you can say these are reactivity of this organometallic compounds. It depends on the ionic character of the metal. So let's say the organometallic compounds, organometallic compounds are versatile reagents. Compounds are versatile reagents. Okay, and their reactivity depends on reactivity. Their reactivity depends on the nature of the metal atom linked with the carbon atom. Okay, so thereby the reactivity decreases with a decrease in electropositive character metal. So you can say that thereby the steady decrease in character, steady decrease in reactivity, a steady decrease in reactivity is found. Okay, is observed with decrease in the electropositive character of the electropositive character of the metal. Okay. character of the metal. So the reactivity, reactivity of the organometallic compounds depends on the electropositive character of the metal. Okay. So let's see how the ionic character of the metal. Let's say metal here, an ionic character of the electropositive compounds. Let's say percentage. So here we have metal here, so potassium, sodium, lithium, magnesium, zinc, and cadmium. Okay, let's see most of the organometallic compounds. Metals are like it. Their ionic character is 51%, 47%, 43, 35, decreasing. Okay, 18. Cadmium is 15. Okay, so ionic character. More ionic character means more reactive. Less ionic character means less reactive. Okay, so depending on the nature of the metal ionic character, organometallic compounds also, reactivity of the organic compounds also determined. Okay, so what I want to say that the reactivity of organometallic compounds are depends on the nature of the ionic character of the metals. So more ionic character of the metal are more reactive of the organic compounds. So let us see how they defend. Okay. So we have different types of metal ionic character. We have potassium. So potassium and this potassiums and sodium and potassium are salt-like compounds. And they are very highly reactive. So the organic compounds, the organometallic compounds, organometallic compounds of sodium and potassium, of sodium and potassium are salt-like compounds, are salt-like compounds. Okay. So they are insoluble in polar solvent, which are insoluble in non-polar solvents, but soluble in polar solvent like water, non-polar solvents. Okay, so sodium and potassium compounds, organic metallic compounds are salt-like compounds, and they are insoluble in non-polar solvent. And then compounds for magnesium, less positive, less electropositive as compared to sodium potassium. Elements like magnesium and zinc. So they are less electropositive as compared to sodium and potassium. Are essentially covalent. They are essentially the elements. Those of the organometallic compounds of less electropositive elements, magnesium and zinc, are essentially covalent. They are not salt-like. They are essentially covalent compounds. Okay, this organometallic compounds of potassium and sodium are salt-like, and magnesium and are covalent compounds, are soluble in ether. Okay, and soluble in say for example in ether. Okay, they are also soluble in non-polar solvents. Okay, so there is some difference between these having highly ionic character, percentile character like sodium, potassium, and compared to magnesium. So reactivity of organometallic compounds can be correlated with their ionic character. So I want to say that the reactivity of organometallic compounds can be correlated with their ionic character. Okay, so I can write down the reactivity of organometallic compounds organometallic compounds are correlated with their with the ionic character of the metals. Okay, ionic character of the metals. So more ionic character, more reactive. So the compounds of sodium and potassium are by far the most reactive compounds of organometallic compounds of sodium and potassium are by far the most reactive. Even the gases fire also. For example, they are very reactive, and for example, these organometallic compounds are spontaneously inflammable, may spontaneously inflammable, getting fire. Okay, you might give it outside in the humidity, they can expose to air, they can catch fire. Okay, highly spontaneously inflammable in the air. Okay, so highly reactive. Whereas organometallic compound of organomagnesium and organozinc compounds react with are less reactive. They can react with oxygen. Okay, even lithium compounds are more reactive than organo as compared to their ionic character. These lithium compounds are more reactive than organomagnesium. Say organomagnesium compound like Grignard reagents. These are okay. And even cadmium compounds are very less reactive, and they do not react with ketones also. The organometallic compounds of cadmium are very less reactive, so they cannot react with ketones also. So one compound, the organometallic compounds which are widely used are Grignard reagents, say like RMGX. Okay. So here R become carbocation and MGX like this, and these organolithium compounds, lithium compounds, so like alkyl lithium or aryl lithium, so like phenyl lithium, or you can say butyl lithium, BULI, and then or you can say phenyl lithium. Okay, these are also very reactive as compared to these Grignard reagents. Alkyl lithium or aryl lithium are more reactive than Grignard reagents. Then we can have organocopher compounds, organocopher compounds. So these are organometallic compounds which are very useful in organic synthesis. So RCU, organic compounds, or lithium. Another one is lithium organic cuprate. Okay, cuprate. So for example, R2CuLi, lithium dialkyl cuprate. Okay, so these are the reactive organic metallic compounds which are used for synthesis of these organic materials. Okay, so what I want to say, in the organometallic compounds, the activity depends on the ionic character of the metals. More ionic character, more reactive of the organometallic compounds having the metals. Okay, so these are about the reactivity. No, we can have two types of carbanions can be used, as reactivity of carbanions can be used in two types. So what are there? Depends on the carbanions can act as the bases, carbanion act as the nucleophiles. Okay, so there are two cases where broadly expressed in two basic types of reactions: the stability and the reactivity of carbanions carbonyls, maybe broadly divided, maybe broadly classified, maybe broadly classified into two types. It might be classified into two basic types of reactions. Two basic types of reactions. Okay. So we can have two basic types. First one is carbanion as bases, acting as bases, and second was carbanion. Okay, carbanions as nucleophiles. Okay, so this they can behave depending on the activity of the carbanions. They can act as bases or phosphorus. We can discuss the first case, so like this carbanion, say like this. So we can have this carbanion. Can act as a carbanion, act as a base, reacts with photon donor acid. As you can say, photon donor is the acid, organic acid. So like they can attack this one and they can get another carbanion. Okay. So here you can say this C is, and then we have this one. So conjugate acid. So in the acid base, conjugate acid plus or another carbanion. Okay. So this here carbanion act as a base. Here acting as a base to extract the proton from the acid to get conjugate acid. So this is acid base equilibrium. Okay. Acid base equilibrium. So in this case, what I'm to say that carbanions can act as bases also. So that they can extract the proton to give the conjugate acid. Then you can have carbanion as nucleophiles. Nucleophiles very common in organic chemistry. So they can act in many reactions. They are found. Okay, so they are highly nucleophiles. Carbanion can act in nucleophiles. They can add addition to many. Can add to many double bond compounds like carbonyl compounds, heteroatoms, or even in double bond or triple bond like this. So they can undergo many reactions. So depending, they can act as a nucleophiles. Okay. So you can have different types of reactions, such as Organometallic condensation, aldol condensation, Parkin reactions, Wittig reactions, etc. So many reactions are named reactions are here, where carbanion act as the nucleophiles. Okay, these are about the types of nucleophiles, types of carbanions, which are classified in two types. First one is carbanion as bases and carbanion as nucleophiles. Now let's come to reactions of carbanions. So reactions of carbanions, there are can be classified into four major types of reactions of carbanions. Okay. So there are generally we can have broadly we can classify to many types of reactions. First one is addition reactions. So here addition carbonyl, I have told like that carbanion can add to this carbon hetero multiple bonds to give this way. Okay. So R O negative charge. Okay. So this another one addition reactions. I'm just giving you another one elimination reactions. So here we found in the case of E1CB. Okay, E1CB conjugate base elimination reactions. So here we have this type of reactions. R, one example I'm giving here. Yeah, there's another. Okay, this is a proton reacts with CH2. Okay, let's say living group L. Okay, so you can write this way. Yeah. So here in the base extract proton. So first step is extract the proton. Okay, so it gives a carbanion fast. So carbanion is formed first, and then we have the second step is the loss of this leaving group. So it is elimination reactions, okay, with a double bond here. So this is E1 formation of E1 CB. So here conjugate base is formed here. So when base has affected the proton, we got a conjugate base, and then lost this leaving group, you got a final product. So this is a elimination reaction. For elimination reactions can take place, carbanion can react like this also. Then third one is displacement reactions. Displacement. Third one is displacement reactions. So that attack to the carbon bond. Okay, let's say one example I'm giving here, just general examples. So let's say this is the leaving group. So I take here, like those like this. So you can have R plus X negative. Okay. So this displaced X is displaced by this R this carbanion. So this is another example. I'm giving general examples. Sorry. So reactions of carbanion can take place: addition, elimination, displacement, and finally we have combination with a positive species. Combination with a positive species. So we get from this we get neutral compounds. So R plus, say let's say electrophilic compound, or you can say X, or proton also you can have like this. So you can have RX, RE, or RX, or RS. Okay. So you combine with the electropositive species. So there are 4 reactions of carbanions. So first one, addition, elimination, displacement, and combination with the positive species. So now let's come to the rearrangement of carbanions. The rearrangement of carbanions are less important as compared to the rearrangement of carbocations. So let's have rearrangement of carbanions. So carbanion can undergo rearrangements. Good. So first one is a Favorsky rearrangement. Where the alpha haloketones undergo rearrangement in presence of alkoxide ion to give the carboxylic esters, okay, derivatives. So you can write the conversion of the base catalyzed conversion of alpha haloketones in presence of, you can say in presence of alkoxide ion, in presence of alkoxide ions, say OR negative charge. Okay, alkoxide ion to conversion of alpha haloketones to carboxylic acid derivatives. Carboxylic acid derivatives can be acid, esters, or amide. Okay, depending on the nature of the alkoxide ions. Derivatives is known as Favorsky rearrangement. Okay, Favorsky rearrangement. Okay, I'm listing again. The base catalyzed conversion of alpha haloketones in presence of alkoxide ions to carboxylic acid derivative is known as Favorsky rearrangement. Okay, I just write, let's say RCH2. They have some acidic molecules. Acidic atom should be here, and another one CH. Here X is a leaving group, and R. Okay, so it's alpha halo. X is halogen. Okay, you can say this alpha version, alpha haloketones. So this name is alpha haloketones in presence of OR equal 1 alkoxide compound. So it can go to give the esters, okay. R O C O ester will come, and CH R and the CH2 R, okay. So here we have R same, okay. We are not same R prime, then we have different products. So we got this ester, okay. Here ester. If we use OS group, then you got a acid and or you can say amine, NH2 group or amine, and RNA this thing, and primary amine or amine. Then we got a amides, okay. Depending this will come to NH2. So depending on this nature of this addition of this alkoxide, if we use alkoxide, then we got ester. Hydroxide, we got the acids, and amine or ammonia will give the amides, okay. So depending on this. But in the case of cyclic compounds, they can undergo ring contractions takes place. So in the case of cyclic alpha haloketones undergo ring contractions. So for example, say 6-member ring, alpha halo, alpha chloro cyclohexanon. So let's say this is the methoxide, okay. This is the methanol, in presence of methanol, will give this ring contraction to from 6-member ring to comes to CO2, CH3. This cyclic ester, 5-member rings, cyclic ester. So it depends on ring contraction in the case of cyclic alpha haloketones, and ring contraction takes place. So from here I am giving one example for this 6-member ring to 5-member ring. So let's see the mechanism of the Favorsky rearrangement. Favorsky rearrangement mechanism of the Favorsky rearrangement. Okay. So first let's say R CH, okay, CH2, and then we have carbonyl group. Then we have these alpha halo compounds. These are alpha halo ketones, okay. Alpha halo ketone. So so in presence of say alkoxide R1, so after the proton here, so it gives a carbanion fast formation of carbanion is formed, and then COO and CH R, okay, then X. So you takes this here, then lost this halogen, okay. So you combine together, we got a cyclopropanol ring, 3-member ring. So you can have C double O, CH R, this is linked together, okay, yeah. Okay. Got a cyclopropanol intermediate. Cyclopropanol, ONE, okay, intermediate. So here, this can be attacked by alkoxide ion. So let's say this attack here. So first, we can form an intermediate. So here, OR and the O negative charge. Then we have this cyclic CR, okay. So now return back this charge, return back. So it can return back. It can drop on the ring. So we got this. Okay, this one will come broken here. So R, CH, negative charge, and you can have CH. So here broken down here, CH, or you can just C, O, or prime. Okay, here O prime, and this CH R. Okay. So then pick up this. You can see this one. Okay. So you can pick up the proton. Then we can have RCH2, CH R. Then we have CO2 R prime. Okay, this ester is formed. So this is the mechanism. First, I'm fitting again the mechanism. First, alkoxide ion pick up the proton to get the carbon ion. The carbon attack to this alpha position of the ketone. Then where halogen is lost, halide is lost. Then you got a cyclopropanol ring. then again attacked by alkoxide ion to the carbonyl group, then again return back the anion, then lost that ring is broken down, the bond is broken down, cleavage takes place to get open sand, then pick up the proton, this proton pick up by this carbon ion, got a final product. So we got an ester. So ester. So phyloketones, conversion of phyloketones to ester is known as favorite rearrangement. This one also we can have when for cyclic phyloketones. So I'll get the mechanism for cyclic alpha halogen ketone. Okay, let's say this 6-membering. Okay, this Cl and this hydrogen are here. In presence of this OCH3, let us say the alkoxide methoxide ion attack here. So we got a fast stable formation of carbon ion here, and Cl. Okay, then attack this attack here, like cyclization takes place. So we got a cyclopropane, just like earlier cases. Then attack by OCH3 attack here, again attack, and then this one intermediate O negative charge OCH3, then here, so coming back here, so broken down here, so we get again the cleavage of the bond takes place, so we get a 5-member ring. So here negative charge here, this become carbon here, this become OCH3. Okay, so then pick up the photon, earlier gases, so it becomes as 5-member ring ester. Okay, CO2 Me, okay, CH3. So here this is a mechanism for the cyclic ketones. If there is no alpha acidic ketone, like then we have another type of reaction. For example, there is no alpha acidic here, like X, the R. Okay, there is no CH2 group here, like earlier on, RCH2, the alpha, CX. Okay, here the CH group here, but there is no hydrogen here in this case. So in this case, the rearrangement also can take place. So let's say OR prime negative charge direct attack to the carbonyl groups. So you can have R, C, O negative charge. So here OR1, and then CH, X, then R. Okay. So coming back here, the rearrangement takes place. Then loss is okay. So here there is no alpha acidic atom, alpha hydrogen atom. So in this case we got another this rearrangement takes place. R1, O, ester will give CH, R come here, R here, and R here. Okay. So there is also another Fibonacci type rearrangement, but here no alpha hydrogen atom, acidic atom. So in this is mostly known as semi-benzylic rearrangement. Semi-benzylic rearrangement. Okay. So this is just modification of this Fibonacci rearrangement. So here there is no alpha. So rearrangement can take place where no alpha acidic hydrogen atom. Okay. So this is about the Fibonacci rearrangement. Now let's come to Somlet-Hausser rearrangement. Another rearrangement of carbon ions using the Somlet-Hausser rearrangement. Somlet-Hausser rearrangement. Okay. So here, this is the rearrangement. Okay. Here, here the benzyl, quaternary benzyl, ammonium salt are converted into this thing substituted benzyl elements. So here I can say benzyl quaternary ammonium salt. Let's say CH2 benzyl, then we have quaternary CH3, let's say CH3 quaternary salt. So it becomes positive charge, let's say methyl iodide. Okay. So here benzyl quaternary ammonium salt. This benzyl group, you can say benzyl quaternary ammonium salt, benzyl quaternary ammonium salt. Undergo rearrangement in presence of strong base. Ammonium salt undergo rearrangement in presence of strong base like sodium amide, sodamide. This acting as a very strong amide base. Okay, so here conversion takes place to give the substituted benzyl amines. Okay, and C3. So here, so this is known as Somley-Hauser rearrangement. So conversion of, you can write that, conversion of benzyl quaternary ammonium salt, benzyl quaternary ammonium salt into the benzyl, substituted benzyl amines. These benzyl amines in presence of alkali metal amides. Okay, so here you use the sodamide. Okay, sodium amide is known as Somley-Hauser rearrangement. Okay, so conversion of benzyl quaternary ammonium salt with sodium amide into benzyl amine substituted. Okay, so let's see how the reaction or mechanism takes place. Okay, but the product here also, in one case here is that it is to be noted that the product here is also a benzyl, so this can undergo further rearrangement. So suppose if we use this one, reactive with methyl iodide, CH3I, so we got another starting material. Okay, so you get CH2, so you can take here, so you get here. So another quaternary salt will give CH3, positive charge, okay, I. So quaternary. So another benzyl quaternary ammonium salt. Okay, you can get like this one. So here you can get Somley-Hauser rearrangement. Okay, by reacting with sodium amides. Okay, so product will be substituted CH3, and you can have CH2 and CH3 like this. So another product. So this can continue again and so on until unless the autopoison is blocked. If the autopoison is blocked, then the reaction stops. Until unless this can undergo by using alkylation, using the methyl iodide. So Hauser rearrangement can undergo until unless the autopoison is blocked. So let us see the mechanism how the Somley-Hauser rearrangement takes place. Mechanism of Somley-Hauser rearrangement. Okay. So let's see. So let's say this one, and CH2 and CH3, okay, quaternary ammonium salt. Okay. So in presence of sodium amide, it's a strong base, so I extract the proton from here, so I get a carbanion. You got a carbanion fast carbanion form, CH, okay, CH negative charge here, and then N CH3, and we have CH2. This hydrogen is picked up by this base and attack here. So you got this rearrangement takes place. You got another carbanion. You can write this way. So you can write this got a carbanion. This becomes CH2 here. So you pick up and it becomes CH2 here. Then we have N CH3, and this becomes CH2, you get the cells. Okay. So now you pick up this one. Okay, you take this one and this one come this way. So now this carbon ion attack to the ring. So we got this an intermediate. So here. So we got this CH2. Then we got this link with this CH2, and now it comes 2 CH3 here, 2 CH3, CH3. So we have hydrogen here. So lost this one. Take here. So we got this one. So we got this CH3 product. Okay, CH3, and this is benzyl amine. Okay, CH3, CH3. So this is the mechanism of the Sommer-Hausser rearrangement. So I'm looking again. First, acidic proton is picked up to get a carbon ion. This carbon pick up the proton from here, so it gives another carbon ion here. Then attack this ring, so it goes like this. So then it comes to give an intermediate, which lost the which transfer the shift express to CH3. So we got the benzyl. So that benzyl amines. Okay. So these are some Hausser rearrangement mechanism. It can be almost similar with the stable rearrangements. Another one, if there is no for this one, link with another quaternary ammonium chain, let's say R1, R2, R3, okay, positives. And then we react this sodium amide. Another modification of here, actually with electron withdrawing grooves, electron withdrawing groove. Okay, so here this is sodium amide attacks from here. Got a first carbon ion forms, then we got R1, R2, R3. Okay, they pick up this alkyl group, so we got this one. Okay, so now product will be X, CH, so we pick up the R3 and R1, R2. So the another rearrangement of carbon ions. It's also known as Stebbins rearrangement. This is known as Stebbins rearrangements. Stebbins rearrangement. Okay. So this is almost similar with Sommer-Hausser rearrangement, but we are in the Stebbins rearrangement, quaternary ammonium salt containing an electron withdrawing group X is there. And one of the carbon atom attaches to nitrogen. Electron withdrawing group and one of the carbon atom attaches to nitrogen will get that place. So this gives here a tertiary amine. Another it gives a tertiary amine. So it gives tertiary amine. Okay. So this type of comparison known as Stebbins rearrangement. So we can compare this with the Stebbins rearrangement. So this is about Sommer-Hausser rearrangement, rearrangement of carbon ions. Too. Last one we can have Niebuhr rearrangement. Okay. Another one, Niebuhr rearrangement. Niebuhr rearrangement. So here, these sulfonic esters of ketones are converted into alpha-aminoketones. Okay. Niebuhr rearrangement. Niebuhr rearrangement. So here, alpha-aminoketones are formed from the sulfonic esters of ketones by reacting with potassium hydroxide. Okay. So let's say the formation of or conversion of sulfonic esters of ketones with potassium tertiary phosphide or potassium hydroxide, potassium hydroxide. You can say strong base, KOET, okay, potassium hydroxide, or you can use sodium hydroxide, another alkoxide ion, followed by hydrolysis, conversion of non-esters of ketones with hydroxide, followed by hydrolysis to give into conversion of sulfonic esters into alpha-aminoketones. aminoketones is known as never rearrangement. Okay, never rearrangement. So we can write this sulfonic ester SO2. Okay, it's a phenyl group. Autosyl group OTS. Okay. SO2 OTS. This is OTS sulfonic autosyl groups. We actually say R. Okay. So here conversion of this this can be obtained from ketoxams. CH2 C R and OS. Okay. This is ketoxams. Ketoxam. Okay. This is sulfonic esters of ketoxam converted by reacting with toluene sulfonic chloride VSSO2Cl. Toluene sulfonic chloride or sulfonic chloride reacts with ketoxam to get this sulfonic esters of ketoxam. So this reaction with sodium hydroxide of OET or potassium hydroxide, so they convert it to in presence of hydrolysis followed by hydrolysis. Okay, first, second, followed by hydrolysis will give this alpha aminoketone. Aminoketone COR. Okay. So here in alpha position they have amino group. So it is alpha aminoketone. So this is rearrangement. So I'm fitting again the alpha aminoketones maybe preferred by the treatment of sulfonic esters of ketoxams with potassium or sodium hydroxide followed by hydrolysis. Okay, so the conversion of this sulfonic esters to alpha aminoketones in presence of the hydroxide ion is known as never rearrangement. So let's see the mechanism of this. Mechanism is really simple. So mechanism of the reactions of never rearrangement. So here first the base hydroxide ion after the proton. This is the R mechanism of the reactions. So here RCH2, SSC and OTS, the polysulfurine or reaction with base hydroxide ion. So extract the proton from here. First we got a carbon ion here, then C, R, then N, OTS. Okay, then ring circulates to give azidine intermediate. So this gives minus OTS. So silent got. So we got a this three-member ring got azidine intermediate is formed. Okay. So this is azidine intermediate. Azidine intermediate is formed. Then followed by hydrolysis. Followed by hydrolysis by water. Water attack here. So you get this one. So you got R, CH, C, you can say water, O is positive charge here, then R, then we get and negative charge. So if we get the photon from here, so it comes, so here you can tell R, CH, and you can write OH, then R, you can have NH, okay. C, NH. I think you can see it's not. So now is R. Okay. So now coming back this one. So for this transfer, so it comes to this. So we got finally we got this R, CH, NH2, okay. Then this comes ketone, and then R. Okay. So this is the product. Okay. So we got a amino alpha aminoketones. So conversion of sulfonic esters of ketoxams in the presence of hydroxide ion to give the alpha aminoketones is known as never rearrangement. So this is about the carbanions in mechanisms, their mechanisms. So we have discussed now reactions and rearrangements and reactivity of the carbonyls. So today we have discussed the reactivity and effect of carbonyls in organometallic chemistry. So they can be used as organometallic compounds, very useful for organic synthesis. Then we have reactions of these carbonyls. So I'm giving summarize today's lectures. Okay. So reactions reactions of carbonyls, we can have addition, then rearrangement, then displacement, and finally combination. Then rearrangement. Finally, we have rearrangements of carbonyls. They can have fibrodisk rearrangement. Here are phyloketones are converted into esters or carboxylic derivatives by presence of alkoxide ion. Then we have Schönbrand-Hausser rearrangements, where in this case the benzyl quaternary ammonium salts are converted into substituted benzyl amines by reacting with strong base like sodium amide. Okay. Then finally we have liver rearrangements, where sulfonic esters of ketoenzymes are reacted with potassium hydroxide to give alpha aminoketone. So these are the carbonyls intermediates. Okay. So today we'll wind up here. So I think we have covered the syllabus. So you check this thing. Okay. Thank you all.